How's it going? My name's Adam. A lot of people call me Skevy. That's my Twitter handle. I'm a principal software engineer at Airbnb working on our GraphQL platform. I was prepping for this talk and I was looking back at my tweets, and I'll date myself a little bit. I've literally been working with GraphQL since it was first open sourced. This is like a tweet after I contributed the first implementation. It's changed many times since, but the first implementation of subscriptions in the reference spec. So, been working with GraphQL a long time. Love GraphQL. It's pretty much at this point defined like most of my career. And I've talked a little bit about Airbnb's GraphQL platform before. Is there any chance we could close that door? Thank you very much. Sorry. No. I've talked a bit about our GraphQL platform before, but we haven't said much publicly since 2020. Some things have definitely stayed the same, but we've learned a lot in the last 5 or 6 years that we've been working on it. So I'm really excited to be here today to chat a bit about how we've scaled this system. We have a ton of traffic, more than 1,000 engineers working with it every day. I think Rami in his earlier talk said we have 130, somewhere between 130 and 150 teams. So it's really kind of taken over a lot of how we do backend development at Airbnb. So GraphQL. We're at a GraphQL conference. I don't need to tell you what GraphQL is, and I think we all really understand the benefits, right? Unified schema, client-driven queries, type safety across the stack. But when you go to adopt this at a large scale, how do you do it? And I think that if I was giving this talk 8 years ago, you'd be on the edge of your seats, right? You'd be like, hey, he's from Airbnb. He's going to tell you all about how they scale it or whatever, right? But like at this point, everyone kind of knows what the general best practices are, at least at a high level from an architectural perspective. GraphQL outside of Meta has been maturing for a decade, and the community has a lot of answers. So these days, there are essentially 2 main paths, I think, that most folks take, right? The first common path, which is maybe not quite as popular anymore, but I definitely think people still use it, is using GraphQL really as this like microservice gateway. This approach keeps GraphQL at the edge, translates queries to services in your mesh, and usually this gateway tends to be maybe a bit configuration driven. The schema might be auto-generated from the services that the gateway fronts. And usually, those services vend like OpenAPI or gRPC or Thrift Schema or something like that, and you kind of stitch it all together, right? And this works really well when you have strong service boundaries already. So if you follow kind of the domain-driven design model of building your backends, this works pretty well. And so you get a really solid graph that can be built this way and largely keep a lot of the underlying service infra kind of unchanged. The other primary path that I think lots of folks will talk about is GraphQL federation, right? So with federation, you're kind of breaking these things into subgraphs, each owned by different teams. Each subgraph tends to be kind of a microservice in and of itself, so teams kind of get full autonomy of managing that area of the subgraph. And then this really smart router doing all kinds of crazy query planning things, stitches that all together. Apollo, WonderGraph, others have built really impressive platforms based on this model, and it works really well for a lot of companies. But there's a third way that doesn't really get the same level of attention, especially when we're talking about like enterprise GraphQL, which is a deliberate kind of monolithic GraphQL server. Now, is there a reason for that? I think monoliths seem great in theory. And I think it's why most folks, if you're starting a startup or something, you start out hopefully with a monolith. You're not building like 1,000 microservices right off the bat. And the reason why is because it's simple, right? There's one runtime, one graph, strong boundaries. But lurking in this initial simplicity is what I call the monolith trap, which is really, I think why a lot of people move to microservices, right? You have this like ungoverned shared runtime that accumulates implicit coupling, a global kind of build and deploy blast radius, a lot of blurred ownership lines as we're trying to scale it through the teams. And then of course you have like kind of how do you actually scale it from like a performance perspective, right? So resource contention, kind of noisy neighbor problems. And the reflex response then from teams is generally that they have to split the monolith, right? And they build microservices. So at Airbnb, circa 2019, a bit after Airbnb first adopted GraphQL, I was just mentioning this to Michael, our GraphQL implementation was essentially the gateway approach, right? We wrapped our thrift services, we stitched the schemas together, and that worked pretty well for the very initial version, right? It gave our client engineers typed APIs, GraphQL tooling, but we really knew it wasn't the end game. We had this version or this vision of a data mesh, right? Development centered on the graph itself, not on the services that happen to expose GraphQL or expose the data underneath, right? And meanwhile, we had been adopting this microservice approach for several years at that point. I think we started doing microservices around 2015, 2016. And particularly at the presentation or kind of like back end for front end layer, we were really feeling a bit of the microservices hangover, so to speak, right? Every team was reinventing data fetching patterns. There was very low reuse of common patterns across services. Engineers sometimes spent more time, on their service operation, like figuring out how to scale the service, than on business logic. And there was a lot of cognitive overhead of like, should this be a service? Like, it's just a feature. Do we need to build another service? And do I get a promotion if I build another service? And like that's kind of how that went, right? So we were at a crossroads, right? How do we build this data mesh system we were dreaming of? And how could we simplify product development and get the leverage of the monolith without the pain? Could we build a scalable monolith, keeping the graph as this like central key thing, but also keep it safe, right? And scale this thing to many developers. So that takes us to the beginning of 2020, when a small group of engineers set out to build this system. This system is called Viaduct. So Viaduct is Airbnb's GraphQL application platform. And yes, it is a large app on the JVM, built almost 100% in Kotlin, and shipped as a single binary. Our early versions of Viaduct, were not super principled, and we could generally describe it as a bit of standing on the shoulders of giants, on Andy's work and others, kind of a bunch of hacks on top of GraphQL Java. But we found a lot of early success in a few key things. And devs on different teams were starting to catch wind of the project and were really intrigued. And so the few things that we got right from the start was that we vended a single unified schema for Airbnb's entire application ontology. I think a lot of people call these like super graphs and things like that nowadays from the federation approach, but that was like our whole thing, right? We wanted one big, unified schema that everyone could query. We made it really easy to onboard data into the graph. So, we had a lot of these microservices. I said that we had been building them since 2016. We needed to get data into the graph, and so we needed easy connection there. We also, and Rami talked about this earlier. If you didn't get to see his talk, please check it out when the videos are up. But we have a really opinionated way to access data within the graph to power resolvers that need to derive new data, something we call reentrant access or reentrancy. And then we also developed a really deep integration with our internal authorization system that ensured all data was privacy checked during access. So these core concepts of Viaduct really resonated with folks, and usage of Viaduct around 2022 was growing and growing very fast. We needed to get serious about avoiding the monolith trap that we spoke about earlier. And so we really started doing a deep dive into a lot of the core areas of Viaduct where we were having trouble and figuring out how to improve them. So I want to start by talking about, kind of this one core underlying principle that you'll see kind of, threaded through the rest of Viaduct's architecture. So early on, Viaduct had a pretty loose concept of modularity. For instance, we had these team-owned directories. We separated schema and code into these different directory trees. This helped us, ensure we could delegate code reviews and stuff to the right people, but it didn't really do much else. So Viaduct is shaped like a monolith, right? And so there's an opportunity to bring some organization to this monolith. The answer we came up with was to put strong boundaries around the code and the schema within Viaduct. And we call these things tenant modules. This concept is the core underpinning of our ability to scale the system across both the number of developers and also, as you'll hear a little bit later, increased traffic. So what is a tenant module? A tenant module is a strongly defined unit of modularity within Viaduct that contains both schema. This is the schema that's kind of contributed to the graph, and code that implements that schema. And importantly, a tenant module is owned by a single team. This is kind of the crucial building block right there. Engineers write application code inside of these modules. And they can really write, I won't say anything, but they can write a lot of things. We don't put a lot of rules on what people write inside of Viaduct. Of course, we try to tell people they shouldn't be doing, AI inference or something inside of Viaduct, but ultimately they can write whatever business logic they need. Tenants call any service. They read and write from databases. They use caches, and of course, talking about the reentrant data access, they access a lot of other data from the Viaduct graph. So building on top of this, let's go into some of the core monolith problems and how we have worked to solve them. So the first monolith problem, and that for anyone that has worked in a large monolithic application, right, I'm sure you're familiar with, is really kind of tangled dependencies, right? The dreaded spaghetti code. And this comes from hidden coupling through method calls and accidental dependency webs. So imagine we have some code, and we directly call other tenants through imperative function calls. Oh, that doesn't work when I have it on the, never mind. That doesn't work when I have it on the rehearse mode. But you can liken this to, any code you'd see in any type of like MVC type of application, right? You're just like calling some code. You're getting the host ID for the listing, you're getting the user based off of that host ID, and you're returning some value, right? And this works fine in theory, but you can imagine that over time, it becomes really hard to reason about kind of what tenants are calling each other and how data is flowing through the system. You have kind of limited observability and also limited kind of static analysis opportunities to keep the dependency graph sane. So instead, what if we leveraged a GraphQL concept that we already know and understand, the fragment, right? Co-located fragments, it's a theme, it's good. This lets us declare our data needs for our resolver from data that already exists in the graph. So here we already had a host field on the listing and an is superhost field within the user node. We can just tell the Viaduct system to fetch this before running the resolver. And then you just access that data declaratively in the implementation, just like you would in like a typical like GraphQL client. And then this is that reentrant data access. So ultimately, the schema that tenants encapsulate, right, is the interface, just like a microservice, right? And that helps a lot with kind of scaling, how many tenants we have in the system. We then also organize the tenant modules and their schema into a hopefully predictable topology, which we call schema modules. The schema module structure forms a DAG. Presentation can see data and entity. Data can only see entity, right? And then the entity is like kind of the base layer, right? So this structure lets us build this like kind of cohesive and hopefully robust lower layer of data that makes up our core entities. You can think if you use Airbnb, you've got users, we've got listings, we've got reviews, et cetera. And then you can layer more and more product complexity onto those building blocks in the upper layers, right? So in practice, it looks kind of like this, right? Teams kind of extend types upward using the extend type, never by importing code. So, and this is also enforced at CI time with static analysis, build verification, et cetera. Cool. So our next big monolith problem is build times. I said it was a large JVM app, and in particular, it's written in Kotlin. And up until very recently, the Kotlin compiler was very slow. So I don't have any numbers here. Security doesn't like me to put numbers there. But it went up, right? A lot. We had this one global schema. We do a lot of code gen, as you might imagine, because we're in Kotlin and we need types for everything. That meant that basically build times grew kind of linearly with the size of the schema, right? So if you look at what the build looks like in a naive implementation, which is how it used to look at Airbnb, you first kind of build the schema, and then you generate and compile all the types for that schema. That's the red block here. Only then, once you have that, can you compile each tenant against that generated code. And then the schema grows, right? And that first step keeps getting longer and longer, and people, barely build the thing anymore, and it's terrible. Drastically increases the build time critical path. And generally what you want in large builds, right, is parallelization, right? You want to be able to build each tenant individually. And then, so the insight we had, right, was that each tenant didn't need the whole schema. Our schema has 20,000 types, right? Didn't need the whole schema. It only needed a small subset of the entire schema. So that led us to building a concept called a compilation schema. A compilation schema is a projection per module containing the types defined by the module, types referenced by that module, and also any like potentially explicit imports if there's reason for doing that. So we start by gathering the schema from all the tenants and building the global schema. Then we build the compilation schema for a tenant from the global schema, right? This is fast and fully parallelizable. We can do this across all the tenants more or less simultaneously. We then generate and then compile the types for that tenant from the compilation schema instead of the global schema, and then finally compile the tenant module as before. So this drastically improves kind of parallelization in the build, right? And then when the schema changes, right, this, where it really matters too is not just parallelizing the initial build, but avoiding invalidation, right? We have build caches and things like that. We want to avoid invalidation. So when the schema changes here in this system, the invalidation story is much better. If you change types that only tenant A are using, while you rebuild the compilation schema for each tenant, the only compilation schema that changes is the tenant A schema, thus invalidating the tenant A's compile steps. But the compilation schema didn't change for tenant B, C to Z or whatever there, and thus we didn't have to recompile that tenant, right? So it works really well with caching, works really well with parallelization. But compilation schema was only part of the story for improving the build story in Viaduct. If we look at that generate and compile step and look at it more in real life, so to speak, right? Depending on how many types are in the compilation schema for the tenant, the build times on that generated code can vary wildly, right? So is there any opportunity to shorten this time and make our generated code not bloat the build? Let's take the simple listing type from earlier. So we start with this listing type, and then we generate some Kotlin code that looks something like this, a bunch of things elided here. And then that Kotlin code is compiled into JVM bytecode that looks like this, and obviously you don't need to actually see what that is. It's long and crazy, and no one needs to see that. So the generated code was simple and straightforward to generate. So we asked ourselves, could we just skip this compilation step entirely? And we ended up with this really insane solution that Aileen and Rami worked on, where we generate the bytecode directly. So we do not use the Kotlin compiler at all, and we just go straight from schema to bytecode. So this cut compile times, even more, right? Because now you're literally just generating some files, right? Or generating some class files versus actually invoking a full compiler step. So maybe if you want more details on the craziness there, first of all, it will be open sourced, and I'll talk a little bit about that. And then second of all, you can talk to Aileen and Rami about it, because I don't know anything about it. It scares me. That code scares me. So by prioritizing caching and parallelization, we can really kind of avoid the overhead and improve the parallelization of the build. And then we've been able to get these incremental build times much into much more reasonable levels. Moving on to the third monolith problem, no ownership, right? How do you figure out in a monolith, who owns what and what's going on? So especially when things go wrong. So people want to know not just that a certain request is slow, right? But they want to know why it is slow. So something we do in Viaduct is ensure that everything is attributed to a tenant. So when errors are thrown, there's metadata about the tenant that caused the error. When tenants make downstream calls, we instrument all of the clients, and we tag those metrics with the tenant that made the call, so we can easily trace back latency or whatever to the tenant. And we also go so far as to measure blocking CPU time on a tenant-by-tenant basis, right? So we know which tenants might be misbehaving and doing too much work per request. And we can even do crazier things with that data down the line. And we also built a pretty robust internal tracing system built on top of OpenTelemetry. So it's not just distributed tracing in that we trace, calls between different requests, but we actually have a way to output really, really detailed traces for what Viaduct itself does during a request. So we can really leverage this to understand end-to-end what's happening, within a given GraphQL operation. And in these traces, we're able to disambiguate between tenants performing I/O, which is really the common case. We're kind of constantly waiting for downstream services, whether service or database or whatever. And then we separate that from what we call own time, which is the time spent within a tenant during the request that's not spent waiting for a downstream call. So this helps us this is obviously a fake trace, but this you can imagine it looks something like this, and it kind of helps us figure out, where we need to spend time when we're doing performance optimizations. And ultimately, in this system, tenant developers are responsible for their code, right? So just because we have a monolith, right, doesn't mean we're putting all of the responsibility for how everything works and runs on the platform team. Even though I think people on our team would say we still have too much responsibility, but that's a problem, right? That we're continuing to work on. So the final problem I want to talk about is noisy neighbors, right? So we're running a bunch of code in the same JVM process, right? So really anything can happen to some extent. This is especially troublesome if, say, some tenant is doing something particularly bad, like an infinite loop or a memory leak or something like that, right? So there's kind of a traditional method for solving problems like this, in the backend space, I guess, and you think about it with databases, right? And we think about sharding, right? And so that's what we did with Viaduct. We broke Viaduct up into a bunch of individual shards. And for those of you that know about Kubernetes and things like that, these are actually individual Kubernetes apps that can auto-scale themselves, so we actually don't have to strictly balance traffic across the shards. And so we distributed load over these with this dispatcher tier. This dispatcher tier takes a given GraphQL operation and then shuffle shards it over the Viaduct shards. The main idea here is to distribute the hot tenants across the shards, providing some amount of process level isolation for tenants, even though, at the end of the day, we're all kind of running in the same process. So you can imagine that we take in some traffic for some operation, and a certain set of tenants are active for that operation on one shard, but then we'll take in another operation, and a different set of tenants are going to be active on the other shard. And in practice, in real incidents, right, this is shown to drastically reduce the blast radius of bad tenant behavior, reduces overall tail latencies, and really ensures that one bad tenant can't take down the whole system, and will hopefully, if it's bad, it will only have a modest effect on other tenants' performance for a subset of GraphQL operations. So it's not a perfect system, but it's one of those kind of good enough type of things that has helped a lot. Tackling these core monolith problems that in the way we have, right, has worked, right? We can confidently say that we've been able to scale the platform, and much of this adoption has been organic. And there's real value here. Developers appreciate that they're able to focus on code rather than manage and maintain services. They have easy access to data, and overall, it brings some simplicity to their backend architectures. But it would be intellectually dishonest to not also discuss the failures, of which there have been many, the traps we have fallen into over the years. First I want to talk about is that schema quality, at scale is really, really hard. We saw all this organic growth, and it came with inconsistent naming, inconsistent semantics. Rami mentioned earlier that we had, done some server-driven UI things. We've tried that multiple times. And early on, we didn't really enforce robust schema review. So the graph just kept expanding without enough eyes. And the result was poor discoverability, uneven client experience, accidental duplication. So, ultimately, we're working on this now. We're going to continue to invest in this. We need more tools to maintain high schema quality. But this has been a really real struggle for us in this approach, although it's not specifically directly related to the monolith problem, but it's just really hard to scale this type of thing. As Viaduct grew, we really kept encoding a lot of patterns into the framework, right? It's one of those things that if Viaduct was trying to be everything for everybody, right? We had a lot of feature creep and kind of choice overload. And we really kind of, over time, accumulated a lot of ways to do the same thing. So that's definitely been a struggle as well. And I think we optimized for flexibility, but we paid with a lack of clarity. And then, given that framework bloat, right? The performance also degraded as time went on with schema size. The execution model became harder to reason about. So, we have all of this tracing, debugging, et cetera, but it still requires kind of deep knowledge of engine internals in order to, fully debug what's going on in the current state. So we've built a lot of specialized knowledge into the platform itself. And then, running this system at high QPS is just really hard, right? Attribution helped, but like I said, incidents still kind of frequently needed platform deep dives. And I mentioned the build side, right? That the builds went crazy, and ultimately we are still really working on our inner loop, right? We want everything to be fast. I was just listening to a talk about Kotlin compiler plugins and things like that. Like those are approaches we're exploring, right? To keep a lot of what we're trying to do and validations that we're trying to do at build time, like fast and in the inner loop, right? Integrated in the IDE, et cetera. But the size and kind of the shape of our big monolith, right, still demand a huge amount of active investment in DX. So you kind of like this kind of like, admittedly caused a little bit of a feedback loop, right? Schema inconsistencies drive us to add more framework features. Features increase complexity. Complexity raises operational burden. That hurts developer experience, and around we go, right? So starting in 2025, or really 2024, we really decided we needed to break that loop and not just patch it. So we wanted to reset kind of our philosophy. And this year we've done that with a project we call Viaduct Modern. It has a drastically simpler programming model and new architecture. There's only one way to do work. Everything is a resolver in Viaduct Modern. There's no multiple types of resolvers or crazy directives or anything like that. You kind of always know where to put logic and how to test it. We architected the system so that there's a clear split between the engine and the tenant code. So the engine is responsible for handling the GraphQL execution, planning, memoization, a lot of the things that Rami talked about in his talk earlier, whereas the tenants focus on business logic with type-safe generated APIs. So that separation really improves maintainability, makes behavior predictable, and keeps attribution precise. And in modern performance, is architectural, right? Performance by design, not just like a sequence of patches that we've added over time. We have a concept called async memoization that avoids recompute during a request. We do query planning. We're working on figuring out how we hoist dependencies and batch across sibling fields. Sorry, I mentioned Rami's talk already, but he talks a lot about the perf stuff, and Aileen is giving a talk on Wednesday about our batch resolver system, which talks about how we're handling things there. And I really want us to make sure with Viaduct Modern that we prioritize this autonomy piece, right? I mentioned that that tenant developers are responsible for their code. Well, they are, but we need to give them all of the tools that they need to be able to be fully responsible for their code. And so, Viaduct Modern is working on that, or is prioritizing that in its design. And then I briefly kind of mentioned I jumped the gun earlier. Pretty exciting. We're on the cusp of open sourcing Viaduct Modern in the next week or two. And that work has been really great. It's forced us to remove a lot of company-specific magic, tighten the interfaces, and really start to prove that the model stands on its own. And I think like, that's what we're looking for from the community, right? We want a little bit of validation of this approach. I think that's an important thing, as we continue to invest in this at Airbnb. So a few closing thoughts. I think it's an interesting paradox. I talked about both the good things we did and some of the challenges we had. But even with that even with that complexity, Viaduct really saw a lot of broad adoption, right? The monolith approach worked, right? The platform leverage that we get in working inside of a monolith really kind of beat the service sprawl for a lot of engineers at Airbnb. So that's been one takeaway that I've had. And so the trap isn't simply just a monolith, right? The trap is really an ungoverned monolith. And the false dichotomy, I think, that microservices are kind of the only escape from that. A deliberate monolith, one that's built, with boundaries, with governance, and with isolation, can really work at scale. So thank you very much. And any questions? Yeah.
So one of the slides you talked about the build speed slowing down as user grows.
Yeah.
And I think one of the diagrams you had was like global schema.
Mm-hmm.
Can you talk a little bit more about global schema, and does it also slow down as the build size schema grows?
Sure. So when I say global schema, sometimes we call it like total schema in Viaduct parlance, right? It's like you can imagine, say we have 400 tenant modules, right? They all have schema. You can imagine that. This is simplifying it a little bit, but you can imagine that the total schema is all of that schema like concatenated together, right? So concatenation is pretty fast, so that's not really that big of a concern, right? It was what we were doing with that total schema that before we introduced like compilation schema and some of these other things, right? That was really the problem, right? It was that we were doing too much work for, like I mentioned, we have like 20,000 types. It might be a little more than that actually, and we have, hundreds of thousands of fields. I mean, it's just a humongous schema, right? And so, so that's why the total schema mattered in the old way. It matters less as we reduce the amount of work that we're doing from that total schema and keep it more focused on the schema that each individual tenant module cares about.
Okay, so the total schema is just concatenation of small things.
Yeah, basically. Yep. The super graph, to use the Apollo way of saying it. Yeah. Yeah.
Can you tell us a bit about deployments and rollbacks?
Yeah, good question. So we deploy every day. That may sound fast to some of you and slow to others. I think what we found is that we actually like rolling Viaduct out slowly in a normal case, right? We want to roll it out to individual availability zones and things like that and get validation. And so doing a daily deployment, and eventually we may do a twice daily deployment or something like that, works out well for us. But to your point about rollbacks, where speed is much, much more important, that's where we've been spending a lot of time lately. So we can roll back Viaduct in about 10 minutes across, or 15 minutes across all the global zones, if you exclude some of our build issues that is it's not even related to Viaduct. It just has to do with Airbnb's internal CD system. So we're making progress there. And I will say, something that I didn't mention in this talk, but that we're thinking about, for the future is, how could we design a system where we could deploy tenants individually, right? And maybe we still end up doing a kind of big deployment every day or something like that, but just to keep everything kind of modern, right? But certainly for rollbacks, right? That could be super, super useful, right? So we have some early work there, bunch of different ideas, some of which are crazier than others, but yeah. So that's a very active area of work. Yeah.
You mentioned for the noisy neighbors
Yeah.
That you do sharding to mitigate issues.
Yes. Yeah.
Do you have issues then with noisy neighbors going under the radar that you just notice them anymore?
Yeah. So I mentioned that we measure blocking time, right? That's pretty new, and we're starting to measure that now, and kind of get some baselines. So the reason they go under the radar, right, is we have like 5,000 different GraphQL, at least 5,000 different GraphQL operations, and like I said, hundreds of different tenants. And so, anything that's low kind of throughput or something like that is often going to fall under the radar. But by measuring the blocking time, we can start to see outliers, right? That even if they are low throughput, right, they may still be contributing to like bad tail latencies or something like that, right? Because they're doing blocking. A famous example, anonymized, of course, is like we were doing like some kind of crazy geocoding stuff inside of Viaduct, like in a query that literally serves like the main product detail page, and so. That was doing a lot of blocking work, right? That was not just causing performance problems for that surface, but was causing performance problems, at the tail at least for other things, right?
Accumulate if you don't like it.
Exactly. Yeah. So it's a lot of it. So a lot of our strategy here is a lot of learning and things like that, and kind of monitoring, right? I think we want to continue to kind of drive more isolation where we can. Right, in order to make it so that it's kind of safe by default, right, and doesn't rely strictly on kind of monitoring and after the fact investigation. Yeah.
When the code is split into tenants, what is left in the common section that remains?
You mean in the slide that I had?
Yeah, there was like a small bit that was left that was not in the tenants. What is in there?
I think right now. I think if I go back to wherever that was.
I think it's too far back.
Yeah, you're right. It is. Here, it's close. It's right here. Gotta go through all my animations. This one. Okay. Yeah. So it really just doesn't look like this anymore. So there's no longer a common schema directory, right? So it's literally all like projects Viaduct. It's actually projects Viaduct modules, right? And then I mentioned those different schema modules, presentation and data entity. So then each tenant module is organized into one of those schema modules, right? And all the schema, all the code lives in those modules. So there isn't anything left in the common anymore. Yeah. Other questions? Yeah.
So about testing.
Yeah.
If a tenant wants to make a change and they want to test it against all the other tenants, do you have like environments that are separate where they can call the unchanged tenants and things like that?
Yes. Yeah. So a lot of that is standing on like building blocks that we have at Airbnb. So we have a pretty state of the art, actually, thinking about our peer companies, like kind of like shared staging environment where you can deploy your own little instances of Viaduct, right? And then but still use other services or if there's like other, sometimes even other calls to Viaduct, right, can go to the staging environment. So yeah, there are ways to do that. I mean, I think that's another. I will say though, there's still future work there, right? I think treating other tenants kind of as black boxes, right, and making sure that you're structuring your tests around that. It's definitely possible to do, but I think we still have work to do to like push that pattern through the whole code base, right? But yeah. Anyone else? Alrighty. Thank you very much, everybody.